Hello, I'll be presenting some interesting applications of projective geometry which could fit under the umbrella term of computational projective geometry. The two main topics I will talk about are construction of the camera projection matrix and curves and surface modeling and animation. Firstly, the camera projection matrix is one of the fundamental computations, or homographies are actually one of the fundamental computations done in triangle rendering engines used for real-time graphics applications, so video games basically. So I'll go over the full derivation of the camera projection matrix first, and then go into things like Bezier curves and splines, which allow artists to model polynomials by control points, by moving around points. And it turns out modeling them in homogeneous space and projecting them allows you to give the artist more control over the motion of the curve, and I'll show that later. First of all, some background ideas. Instead of simulating the light or anything, most real-time image synthesis relies on homographies, where object surfaces are transformed into triangles. Like you have a polynomial surface description, you tessellate it into triangles, and then you transform them by a homography. Here there's a visual of this. These are just three triangles being rendered. You want to find a homography that can send this frustum volume into this, what is called the canonical view volume. The reason you want to do this is because lines through the origin here corresponds to light incoming to the camera, and you want to send lines through the origin to lines that are parallel to the z-axis, meaning that this is a more convenient coordinate system to do computations in. And the reason why you have a true homography and not just like a 3D to 2D projection is because you want to preserve depth information. So there's an algorithm called depth buffering which allows opaque triangles to be rendered in the correct order, only if you have this information. So that's why you map it to the box. So here's the idea here. So we know that the origin should be mapped probably to the negative z-axis, and the unification of points and directions in projective geometry is really useful for that, because we can just say the homography we want maps this point to this direction. And it's just this, light through the origin, the eye, etc. Now, the computation of the homography, well, we've got a really good tool for this. We know that, well, at least in the extended Euclidean plane, the image of 5 points, no 3 of which are collinear, determines a homography. However, in homogeneous space, in the extended Euclidean space, the image of 5 points determines a unique homography, which allows us to say, we've already got 1, so what if we choose 4 more convenient points that we know the mapping of? So if you look here, there's 1, 2, 3, 4, and these 5 points are in general position, meaning none is an affine combination of the other. If we map these 4 to these 4, and the origin to this direction, we've determined the homography entirely. So we'll just go do that. We choose those 4 points. These are just parameters encoding the shape of the frustum. That's half of the near quad's height. That's half of the near quad's width, half of the near quad's height, the distance to the near quad, and the distance to the far quad, and we get those points and we can map them. Now, to do this, you just do some linear algebra. You know that the linear map of the homogeneous space, which sends these points to these points, is of course A, B inverse. However, these points can be up to any non-zero multiple because they're in homogeneous space. They would represent the same point. So we introduce a new term. Okay, first of all, we introduce the additional point and say, well, if Q has to map to Q prime, up to a multiple, of course, we can say these 4 can be up to a multiple, and we write that as a matrix equation. This is the diagonal matrix formed from lambda 1, 2, 3, and 4, being the weights for the columns being the image points, and just rearrange, do some matrix algebra. This is in generality, but you can do this specifically for the frustum volume problem, which I did first, to derive this camera matrix here. By rearrangement, you get this nice relationship between the ith component of these two vectors, to get the weight of the column vector here, to actually just plug this back in. I use symbolic algebra software, so I don't have to do this. It all expands down into this nice matrix, which, plug it in, and it just works, which is really nice because we've defined now a general homography definition so that you can interpolate the homography instead of just defining one specifically for the shape of the camera frustum. So here's the function signature. If you don't know C programming, this just says it returns a 4x4 matrix, it gets the 5 points, and it takes the 5 images, takes the 5 points in images, and just computes the homography, and you can use that transformed shapes in your scene. And it will be more useful to showcase this in a 3D application. So we've got this. First of all, I will go over here. This showcases the frustum mapping to the box. I'll select it. One by one, I am mapping each point to its relevant point on the box, and then computing the homography, and so it animates it. And if you look forward on, it should be the same as when you look here, but it's probably going to be more interesting to look at it with some more complicated objects that you might see in a video game, like these brick bunnies. These have complicated shader effects, everything, so it all works the same. You transform the triangles, put them on the screen, do shader equations. If you don't know what this means, it's just getting color from each triangle and putting it on the screen. So first of all, you need to do the transformation. So I'm going to select this one, and I'm going to just show them being transformed over here, and transform back. There they are. What's interesting is that if you look at this like a television screen, the projection shouldn't change anything. It should kind of look the same, because this is roughly orthographically projected from this point of view. So, project them, project, 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 compute. It looks almost like it should be the way it is now. But it's an illusion. If you look from the side, they are back to being projected. So put them back. And might as well segue into curves and surfaces now that we've done camera projection matrices. This is just the basic idea of embedding a plane in a homogeneous space and then getting the curve that is the intersection of a curve in homogeneous space with that plane. And you can see this it's kind of like comics. So I'll go back to this. Curves and surfaces in modeling and animation. This stuff is really interesting. Let's see. So we've looked at transformations. What are some applications of projective geometry to object modeling? In film, all of Pixar's characters, there's Toy Story, there's Woody and Buzz from Toy Story 1, until Toy Story 2, not including it, were modeled with non-uniform rational B-spline surfaces, which is a horrible name for piecewise rational spline surfaces, which is also a horrible name. These are modeled in homogeneous space and projected down into 3D space. And I'll explain what that means later. They don't use them anymore because they're very hard to actually model geometrically animated things. People actually had to go in and edit Woody's face in processing to actually get the seams of it to match up and to have at least like C2 continuity or whatever would look good. Anyway, other applications of curves and surface modeling is computer-aided geometric design. This is the Citroën DS. It's a French car from, I think, the 50s, which was one of the first ones modeled with NURBS surfaces, which are the same ones that are used to model the face of Woody here and the face of Buzz. Also, NURBS surfaces were used for Frank Gehry's museum, Guggenheim Bilbao. I think that's how you pronounce it. There's this terrifying spider here as well. I don't know why. I should probably explain what a NURBS surface is, but there's a progression of ideas that builds up to that, which I will work through. So, yeah, first of all, splines can model piecewise polynomial curves with a chosen level of continuity. You can use homogeneous coordinates to generalize those to rational curves, and then what I said about NURBS surfaces developed in the car and aircraft industries. It's a bit of history. and there's a technical definition for NURBS there. So if you've ever used software like this, which has a pen tool, where you can click and drag around points and then make nice curves like an Illustrator and Photoshop, it's a similar set of ideas here. These two diagrams showcase two these are Bezier curves in homogeneous space projected into this space. And as you can see here, Bezier curves are defined by a recursive geometric interpolation, which means take these 2 points, maybe that's 4/5 through there, maybe that's 4/5 through there, let's just say it's in perspective so it doesn't look right, and this is 4/5 from there to there, 4/5 from there to there, and 4/5 from there to there, and as you range that t parameter from 0 to 1, so that's 4/5 in the range 0 to 1, range it from 0 to 1, and you get, it spans this nice curve. It gives you geometric control over the definition of a polynomial. And then, with homogeneous coordinates, you have control over a rational polynomial. However, there's also something really cool about these, which is why they're used in a lot of artistic software. Here's a visualization of the t parameter ranging from 0 to 1. You can drag this around and see that it is projected. Here is a piecewise linear function. You can see that geometrically it doesn't really give you any more control over the shape of the curve, so it's not very interesting. Here's a piecewise quadratic spline. These take a sequence of points and then turn each window of 3 points into a Bezier curve, a quadratic Bezier, such that you have C1 continuity at the joints. And you can generalize this to a rational quadratic spline. But what's really interesting is that what I just did is change the weight. It still represents the same point when it's projected here, but I changed the weight. And what that does geometrically is makes it look like in the 2D plane, this is actually going closer to that point. Where you can actually see it geometrically embedded in the 3D homogeneous space. So programs like Illustrator can give you control over stuff like this. I'll show you why it's more useful here. See, this can generalize to C2 curves, C2 continuous cubic curves, which are more interesting in the case of describing animation. So these are 4 bunnies going along the animation path. Now, because these are rational cubic splines, we can change the weight vector, the weight of them, which is exactly what's happening over here, except here I don't visualize it because then I'd have to draw something in 4D. It's really nice. You can you can weight each point without adding much more geometry. Without adding any geometry, you have a lot of control over the way that the animation path is curved towards certain points. You can also, of course, drag them around as usual in 3D space, but you have this other degree of freedom, which this is the major type of curve that's used in animation software to describe the path of parts of people's bodies in movies, etc. Yeah. Okay. Here I'm just showcasing the same thing I just showed you in the program. They're also non-planar curves, meaning that they can have non-planar curvature if they're cubic, meaning and they're C2 continuous everywhere. These two properties mean you don't really get visual jolts, which is really nice for things like the motion of robot arms or the motion of characters' arms in Pixar films. Next is the generalization. This is the generalization of those ideas to surfaces. Now, technically, the algorithms are quite a lot more complicated, but the generalization is quite simple. Instead of linear, well, they shouldn't be. Yeah, they were harder to program. Instead of linear interpolation, recursively defined here, where you go some amount there, some amount there, 0.5 there, 0.5 there, 0.5 through there, You do repeated bilinear interpolation, which you take two coordinates, u and v, and you generate a point which is bilinearly interpolated between 4 points here, and then do the same construction and it sweeps out a surface, which would be better to show you in 3D. This is, the UV coordinate is just moving around in a circle to showcase how the algorithm evaluates a point on the surface of this object. So I can move that around, etc. This is not a rational spline surface, this is just a paraboloid. You can drag the control points around and see, you can change it. You can't really give it any cubic-like curvature. Well, it kind of looks like that there. But yeah. Now, finally, what this has worked up to is piecewise rational surfaces. Now, this is the major thing used in computer-aided design software, so quite a lot of objects you see around yourself in the world, like airplane hulls, cars, headphones, water bottles, I'm just looking at things around me, are defined in software like this and then manufactured. Now, as you can see here, we've got a control grid defining a piecewise polynomial surface, well, a rational surface. And you can see here, moving the control points can allow you to control the shape of the object. And in this one here, I haven't moved any of the control points, I've increased the weight of these two. I've increased the weight of this one. And that means that it's gravitated more toward this point, exactly analogously to the animation curve stuff, where I gravitate it toward that point here. And I'll just show this in the actual interactive application. It's a lot of points, so it's hard to actually change it. There we go. Oh, okay, that's not too useful. Okay, here. Yeah, see, look, you just change the extra degree of freedom on this point, and you can have actual nice things like fillets and bends or whatever computer-aided design people use to create objects. It's really cool. I've really enjoyed actually learning all this stuff. It's really fun. Okay. Anyway, of course, this all can be turned into algorithms. You can't really see. These are just, I'm just showing that you can turn all these ideas into algorithms that can compute these, which I've used for the visualizations. Now, some sources and interesting things. This is a really good article from an architect who specifically says in the article, I think, that they are not really a math guy, but they clearly are. It's a really good article that I read, which kind of convinced me to do this topic. This book, I read parts of this book, it's dedicated to this idea and its connection with projective geometry, but goes far further with constructions, like intrinsically defining the construction of rational surface splines by the cross ratio and stuff, which I want to learn later. And this is just a really good interactive diagram-based web primer for learning how Bezier curves work, which I wish that I found before I learnt it somewhere else, because it's really, really good. So, you know, thank you for listening to my presentation. Are there any questions? Okay, thank you.